Okay, so let's put again the second video on what time we got here? A quarter. Um, Apologize for the last um, uh, video lecture. Something went wrong in the last minute and a half of the recording. The camera kicked off, so I'm in a different venue now, and so let's continue on talking about chemistry. So we did talk about the periodic table of elements, the 92 natural elements, and what these symbols mean here. And there's chlorine at standard temperature and pressure, as you mentioned in the last lecture. Chlorine, symbol Cl, is a gas. Here's mercury, Hg. That's the again. That uh, symbol is for the Latin name of mercury, and at standard temperature and pressure, mercury is a liquid. Okay, of the 92 natural occurring elements, 25 are essential to people. And 4 of them are very special, the big 4. They make up about 96% of the weight of the body. And those are carbon, hydrogen, nitrogen, and oxygen. Then we have trace elements that are required only very small amounts, but are still essential for life. Things like molybdenum and copper and selenium, stuff like that. Elements can combine to form compounds, substances that contain 2 or more elements in a fixed ratio. So they, as I say, atoms combine with each other using chemical bonds, which we will be talking about. Okay. Here they are, the 25, and the big 4, as I mentioned: carbon, hydrogen, nitrogen, and oxygen. And then we have a bunch of smaller ones: calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium. Those are in fair concentrations. And then you get the real trace elements: boron, chromium, cobalt, molybdenum, selenium, stuff I was talking about, vanadium, zinc. Okay, well, this is an idea of why you do need some of these trace elements because they cause very dangerous condition. This is iodine. We have a single need of iodine to make thyroid hormone, which is made by the thyroid gland, which is right here. And if we don't get enough iodine, our thyroid will blow up into a big lump, as this woman has. It's called a goiter. Uh, Very rare happens in the United States anymore because they put iodine in salt. And so, and also if you eat a lot of seafood, you never have to worry about it. Okay, and those are iodine-rich foods also: strawberries and eggs. All right, and milk. All right. So as I mentioned, an atom is the smallest unit of matter that still retains the properties of an element. And atoms are composed of subatomic particles: protons, electrons, and neutrons. And these particles have 2 important properties. One is charge. A proton is designated to having a positive charge, and there's only one other type of charge, and that's negative. And electrons are given the negative charge. It could have been the other way around, but that's how people first set things up. So we got to remember that protons are positive, electrons are negative, and neutrons don't have a charge. The other property that's important for these atoms is mass, or weight. We can call it weight, although that's not strictly the way you use weight, but the mass. And so protons and neutrons have mass. Electrons don't have any mass, 0 mass. They are pure energy. And a proton weighs an incredibly tiny fraction of a gram. but all protons weigh the same amount. So we make a new weight unit called atomic mass unit. And so protons weigh 1 atomic mass unit. Um, 2 protons weigh 2 atomic mass units, so on and so forth. All protons weigh the same. And it's true with neutrons also. Neutrons weigh exactly the same amount, or have exactly the same amount of mass as protons, 1. So a nucleus that has 1 proton and 1 neutron would weigh 2. If it had 1 proton, 2 neutrons, it'd be 3. Okay. And remember, elements are defined by how many protons they have in their nucleus. That's what those atomic numbers mean. Hydrogen has 1 proton, so it's atomic number 1. Helium has 2 protons, it's atomic number 2. Carbon has 6 protons, so it's atomic number 6, so on and so forth. Now, okay, and there they are. And we're gonna make believe that atoms are like little solar systems, with the nucleus being the sun, and then the electrons as like planets revolving around the sun. That's not actually correct. It used to be, that was called the Bohr model of the atom. It's not strictly correct. Electrons exist in this electron cloud, this probability cloud around our nucleus. So, but that's hard to envision. So we can think of them as little planets around the nucleus. Okay. So he is a helium nucleus. It has 2 protons, 2 neutrons, 2 electrons. And all helium atoms have 2 protons, but they get a variable amount of neutrons. And these are called isotopes. I think it's in a later slide. Okay. Yeah. So all atoms of a particular element have the same unique number of protons. This is the element atomic number. And coincidentally, it also has the same number of electrons. That atom has the same number of protons as electrons. Atom's mass number is the sum of the number of protons and neutrons. Remember, because electrons don't have any mass. So an isotope is 2 atoms that have the same number of protons. Therefore, they're the same element, but they have variable numbers of neutrons. They have different number of neutrons. And these are called isotopes. So hydrogen, for example, the most common isotope, has no neutrons. It has 1 proton and 1 electron. Then there's a isotope of helium called deuterium that has 1 proton and 1 neutron and weighs 2. Then there's another one called tritium, which has 1 proton and 2 neutrons, and therefore weighs 3. And the mass number on the periodic table is the average of all the isotopes together, how much that atom weighs. A radioactive isotope is one in which the nucleus decays spontaneously. Sometimes neutrons just fly off. And that's not a dangerous type of radioactivity, because neutrons don't have a charge, and therefore they just go right through you and they don't do anything. The dangerous is because of alpha particles. This is a proton and a neutron, and since protons are positively charged, they're dangerous. That's the dangerous type of reactivity, and those kind of isotopes decay into a different atom. You see, the ones lose neutrons, they stay the same element. But if they lose a proton and a neutron, they actually become a different element. Okay. So now we can go into prostate cancer, and I'm not going to go into this too much. It talks more about radioactivity and putting little pieces of radioactivity in the prostate to kill cells. That's a dangerous type of radioactivity. But those are cancer cells, and those are the cells you want to kill. So that's one of the uses of radioactivity. little radioactive seeds inside the prostate. Okay. Okay. Only electrons are directly involved with chemical reactions. Not the protons, not the neutrons, number of electrons. And actually, it's only the outermost electrons that participate in chemical bonds. These are called the valence electrons. And the number of electrons, particularly the number of valence electrons in an atom, determines the chemical properties of that atom. What other atoms do they combine with, and how do they combine with? Chemical reactions enable atoms to transfer or share electrons. They can give away electrons, they can take on electrons, or they can share electrons. And these are the different types. These interactions usually result in atoms staying close together by chemical bonds. And we're going to go over several types of different chemical bonds, depending upon whether the electrons are given up, taken on, or shared. All right. When an atom loses or gains electrons, it becomes electrically charged. So here's the thing. Atoms can take on electrons, and for reasons which I'm going to get to, or they can give up electrons. When they do this, they become electrically charged bodies called ions, and it profoundly changes them. They're no longer the element have the properties that the element had. They're profoundly changed. I'll show you that in a moment. So when an atom gives up an electron, some other atom always gains an electron. Electrons just don't fly around all by themselves. They got to be associated with a nucleus, and so if an atom gives up an electron, some other atom has to pick it up. And that forms what's called an ionic bond. Table salt, sodium chloride, is held together by this type of bond, an ionic bond. So here, well, this animation is not going to work. Here's sodium. It has 11 protons, 11 electrons. Chlorine has 17 protons, 17 electrons. All right. Here's the thing. Sodium is going to give up its electron to chlorine. Why? Well, why does it do that? Well, here's the interesting thing. You see these yellow circles around the atoms. These are called shells, and they're called orbitals that are in shells that hold on to electrons. All right. So we can talk about the closest shell to the nucleus is the first shell. The next is the second shell. The next is the third shell, and there could be a fourth shell, a fifth shell, a sixth shell. All right. Here's the thing. Can only be a certain number of electrons that are held in shells. The first shell can only hold 2 electrons. Why? I have no idea, but that's the way the world works. You just gotta accept it. The first shell holds 2 electrons. If you have 3 or more electrons, you have to put those in the second shell. And the second shell can hold 8 electrons. Again, why? I don't know. But it's important to realize that the first shell only holds 2, the second shell holds 8, and no more. If you want to get another electron, you got to put it in the third shell. All right. So a shell that has the maximum number of electrons that it can hold is called a filled shell. And here's the thing. Atoms want filled valence shells. Remember, the outermost shell is called the valence shell. That could be the first shell, the second shell, the third shell, depending upon how many electrons there are. They want filled valence shells, which is usually 8. For every shell except the first one, that's 8. So this is going to be called the octet rule. Remember, the first shell is filled with 2. Every other shell is filled with 8. Okay. And why do they want filled shells? I don't know. I like to think of it, they're happy. Happiness for an atom is a filled shell. So they would do anything to get a filled shell. It has to do something with stability. So sodium is very unhappy. It has 11 electrons. No, it has 11 protons, but not concerned with those. 11 electrons, 2 in the first, 8 in the second for 10, and 1 more in the third. And it's very unhappy because it wants a fill valence shell and it only has 1 electron in the fill valence shell, so it's 7 away. Chlorine is also unhappy. 17 valence, 17 electrons. 2 in the first, 8 in the second for 10, and 7 in the third. Ooh, so close. There's 1 more, and I can get, a full valence shell. I can be happy. So sodium chloride are made for each other because sodium, and also here's the thing: if you can get rid of the electrons in a shell, it disappears. Again, why I don't know, but it disappears. So if sodium can get rid of that 1 electron, that third shell disappears. And now its second shell is the valence shell. And how many does it have? 8. Happy. All right. Chlorine says, I'll make you a deal. You want to get rid of an electron. Well, I'm dying for an electron. I only need 1 more, and I get a full valence shell. So let me take that electron off your hands. So they do. And when they do, they form a compound called sodium chloride, which is table salt. Okay, here, and this is how profoundly changed these guys are after they do this. Because sodium at standard temperature and pressure, the elemental sodium, is a dangerous metal. It's an explosive metal. It's really dangerous. It comes anywhere near water and it explodes. Chlorine gas, deadly poisonous gas. Okay, they form ionic bond. What do they make? Sodium chloride, table salt. How much more innocuous is table salt? Unless they got high blood pressure, it's just salt. So this is how these elements become profoundly changed when they give up or take electrons, and they become ions. Now sodium is no longer sodium atom; it's sodium ion, Na plus. Chlorine is no longer chlorine; it's chloride ion with a negative charge. Where do these positive negative charges come from? Well, look at sodium. It had 11. Now, atoms are electrically neutral. I should have mentioned this a long time ago. Since atoms have the same number of protons as electrons, they're electrically neutral because they have the same number of positive charges as negative charges. So sodium atom has 11 positive charges, the protons in its nucleus. 11 negative charges, its electrons. Once it gives up an electron, it still has those 11 positives in the nucleus, right? But now how many negative charges is that? 10, not 11. So it has an extra positive charge. So it gets the positive charge, and it's called a cation. All positive ions are called cations, and they've given up electrons. Chlorine now gains electrons. It has 17 positives, 17 negatives. Now it still has 17 positives, but it has 18 negatives, an extra negative. So it becomes gets that negative charge because it has an extra negative charge. And it's called a dog ion. No, not dog. It's called an anion. All negative charges are called anions, and they're all ions that have gained electrons. Okay, so that's an ionic bond. All right. Now, if we go back to the, if we're going to covalent bonds. So here's the thing with this. Let me go back to the chart for a second. Let me show you something about this chart. Oh, wait a minute. They don't put the numbers of the charts, do they? This chart is set up in a particular way. We're going to look at what are called columns. There's going to be column 1, column 2. I don't know why this slide doesn't put those numbers up there, but if you look at the most periodic table evidence, you pull up on the web, it'll have columns. It'll have A columns and B columns. and has 8 A columns. 1, 2. Skip these middle ones here. 3, 4, 5, 6, 7, 8. 8 columns. All the atoms in these columns have something in common. They all have the same number of valence electrons. So all of these, hydrogen, lithium, sodium, potassium, they all have 1 valence electron. This column here has 2 valence electrons. This is 3, 4, 5, 6, 7, 8 valence electrons. That's why they're in those columns. And don't worry about these middle guys for the moment. So here's the thing. They all, the elements in column 1 all have 1 electron, and they're dying to get rid of it, just like hydrogen. So all and then all the elements in column 7 here, they all have 7 valence electrons, and they're dying for 1 more. So elements in column 1 always make ionic bonds with elements in column 7. So we had before sodium chloride. You could have sodium fluoride, sodium bromide, sodium iodide, lithium chloride, lithium iodide, so on and so forth. So they always make ionic bonds with so 1 and 7, they always make ionic bonds with each other. And also in column 2, 2 valence electrons. Is it easier to get 6 or get rid of 2? They get rid of 2. So magnesium can get rid of 2 electrons, give up the 2 chlorides, and form a compound called magnesium chloride. And chloride has 2. So there's 1 magnesium ion and 2 chloride ions make up magnesium chloride. And magnesium becomes is a cation with 2 positives because it's giving up 2 electrons. So it has 2 extra negative charges. So 1 and 2 always make ionic bonds with 7. Okay, let's go back. So let's look at covalent bonds now. When 2 atoms share 1 or more pair of electrons, the covalent bonds are a lot stronger. Ionic bonds are relatively weak because you put them in the water, they break apart. But they break apart pretty easily. Covalent bonds are stronger. And there's actually 2 types of covalent bonds, polar and nonpolar. We're going to get to those. The strongest of the various bonds and hold atoms together in a molecule. A molecule is any 2 or more atoms held together by chemical bonds. And so like 2 hydrogens. Oh, wait. You go back. 2 hydrogens will make a covalent bond together. They both want 1 more valence electron. So they can put them together and share them. So half the time the 2 electrons revolve around 1 hydrogen, and the other half of the time they revolve around the other hydrogen. So they form a molecule called H2. Okay, here's different ways you can designate molecules. There's electron configuration. Here, carbon has 4 valence electrons. So how many electrons does it want to have? It wants to have 8 valence electrons. All right, it only has 4. So it could either try to gain 4 or lose 4, but they generally don't do that. Give away that many electrons. So they share electrons with other atoms. So carbon needs 4. So it makes what's called covalent bond with 1 hydrogen. Now it has 5. Makes another covalent bond with another hydrogen. Now it has 6. Still needs 2 more. Well, now it can share 2 sets of electrons with oxygen. This is called double covalent bond. You can have single, double, triple covalent bonds. sharing one, two, or three pairs of electrons. But there's no such thing as a quadruple. It's only single, double, and triple. And oxygen is atomic number 8. So how many valence electrons does it have? You can figure out mathematically. It has 8 total electrons, right? Okay, there's 2 in the first. That leaves 6. That leaves 6 in the second shell. So how many does it want? Like everybody else, it wants 8, except for hydrogen. Hydrogen is the only one who just wants 1. Everybody else, 2. But everybody else wants 8. So it needs 2 more to get 8. So it forms a double bond, and coincidentally, carbon needs 2 more electrons to fill up its share, so it makes a double bond. And it makes a compound called formaldehyde, CH2O. And there's a space-filling model and a ball and stick model that designate those molecules. And so that's the molecular formula, C2 sub CH sub 2H, CH2O is the called molecular formula. It's what atoms are participating in the molecule and how many of them there are. That above here, the structural formula is how those atoms are connected to each other. And they have to be connected in the proper ways to fill up the valence shells. So you know that oxygen always makes 2 bonds. Why? You need 2 valence electrons. Carbon always makes 4 bonds. Why? Because it needs 4 more valence electrons. Hydrogen only ever makes 1 bond, because it only needs 1 bond to fill up its valence shell, which is the first shell. Okay, so you can tell how many bonds an atom should be expected to make if you know how many valence electrons it has. Okay, and for almost all everybody except for hydrogen, that number is 8. So you take how many valence electrons it has, subtract it from 8, that's how many bonds it makes, right? Okay, now we're going to get into polarity, but before we do that, let me go back. The periodic table of elements, again, to talk about how many bonds these things should make. As I mentioned, carbon has 6 total protons. How many valence electrons it has? 4. 2 in the first, that leaves 4. So how many bonds should it make? 4 from 8 is 4. Makes 4 bonds. Like nitrogen, next door. Atomic number 7. How many valence electrons it has? 2 in the first leaves 5. How many bonds are you expected to make? 5 from 8 is 3. See? But sometimes, and that's called the octet rule. But of course, rules are made to be broken. And sometimes they do. Sometimes nitrogen actually make 4 bonds. And some of these atoms break the octet rule all the time, like phosphorus when we get to that. But anyway, so here's an interesting thing. What about row 8 here? All these guys. How many bonds do they make? Well, let's look at neon, atomic number 10. So it has 10 electrons, 2 in the first, 8 in the second. Well, what's 8 from 8? 0. It already has a filled shell. Matter of fact, all of those elements in row 8 have filled valence shells already. So they're happy, and they don't do chemistry. They don't combine with other atoms. So since they hold themselves aloof from everybody else, and they're all gases at standard temperature and pressure, they're called the noble gases, and they don't do chemistry. So it's fortunate that all the other atoms that don't have filled valence shells want to combine with other atoms to get them, because that makes chemistry possible and that makes life possible. All right. If they were all like helium or neon or argon, there wouldn't be any chemistry on Earth, and life wouldn't have evolved, wouldn't exist. Okay. Okay. Let me get. Uh, okay, so that's about a half hour. So let me go back to where we were, and we'll get started on the next video. We'll get into uh, polarity and the two different types of covalent bonds. So let me stop, and this will be 106 chem 2. Now the first one was really short, 10 minutes long, and it malfunctioned. This one should be okay. So so let me stop recording, and I'll see you later on the next video.